So our topic today is going to be the Doppler effect. It's much easier to hear the Doppler effect than to describe it. So let's take a moment and listen to it. Now listen to what that fire truck was doing. As it came towards us, it appeared that we heard one frequency. But when it was driving away from us, it appeared that we heard a different frequency. The thing was, the fire truck was always letting out the exact same sound the whole time. So what's going on here? So let's take a look at this visualization we have here to the left. What we've got going on is you have this object and it is moving. And as it's moving into its own sound waves. As a result, the ripples are getting closer together. And as a result, the observer at the front is going to have more of the waves hit per second. That's going to be perceived as a higher frequency. The exact opposite is true for our back observer. If we take a look here, they are getting less waves per second because the object is moving away. So we had to take into account the speed of the source in order to determine what frequency we're going to be perceived to be hearing. So if we look at what's happening to the observer in the front, what they're going to perceive is a higher frequency. So the formula for the Doppler effect as they're coming towards you is looking at this new perceived frequency is equal to the original frequency times the speed of sound divided by the speed of sound minus the speed of the object. Now we're going to have a subtraction on the bottom because we're expecting the number to get larger. We're going to expect to see an increased frequency, so a higher pitch. On the opposite, if we have something going away from us, we're going to expect to perceive a lower frequency. So yet again, our f prime is our perceived frequency, which is equal to our original frequency times Vs divided by Vs plus Vo. This is going to give us a smaller number. And just as a reminder, Vo stands for the speed of the object. We've got the speed of sound here. And as a reminder, what that formula is in air, it is going to be Vs is equal to 332 plus 0.6 times the temperature in degrees Celsius. When we talk about our Fs, this is going to be the actual frequency. So whatever the machine is actually doing if you're just standing there and it's not moving. Whereas this right here is going to be the perceived frequency. So when we hear something that's a higher pitch or a lower pitch. So for an example on how to apply this mathematically, an A note, which is 440 hertz, is played by a car driving down the street at 35 meters per second. If the air temperature is negative 18 degrees Celsius, what note do you perceive? Well, we're going to have two answers. We're going to have the note that we perceive that's going to be a little bit higher as it comes towards us, and we're going to have the note that we perceive as it goes away from us. So first thing we need to do is figure out the speed of sound. So Vs is equal to 332 plus 0.6 times negative 18. And when we work this out on the calculator, we get 321.2 meters per second. We know the speed of the object is going to be equal to 35 meters per second. Now we know the frequency is 440 hertz. What we don't know is our perceived frequency. So we're going to have to do this formula twice. One for coming towards us and one for going away. So we'll go ahead and it becomes F is equal to Fs over, Vs minus Vo. And we'll go ahead and plug these numbers in. And when we plug this into our calculator, we get an answer of 493.8 hertz. So that's coming towards. Same idea for going away. The difference is in this case, our formula is going to be f prime is equal to f Vs plus Vo. So yet again, same numbers. And when we plug in we get 396.8 hertz.